TF-IDF can create millions of sparse columns, and PCA forces them dense. Scikit-learn's Truncated SVD compresses that matrix directly into compact text embeddings. You'll learn the shape of a workflow that compresses document text into compact embeddings without making a dense copy. I'm Professor Pi, teaching AI foundations with simple Python. Picture a search index built from thousands of short documents. Every distinct word becomes a column. Most documents touch only a handful of words, so the matrix is mostly zeros. That sparsity is great for memory, until you try to run PCA-style transforms that expect centered, dense arrays. Truncated SVD exists to give us a low-dimensional view without paying the dense penalty. It compresses TF-IDF directly while keeping the sparse representation during training, so you can scale to larger text collections without exploding memory use. Think of Truncated SVD as finding a few latent directions that summarize how words co-occur across documents. Instead of keeping millions of term columns, you keep just a few dense coordinates per document. Those coordinates are compact and ready for nearest neighbor or classification. The trade-off is clear. Fewer components mean smaller embeddings, but less nuance. More components preserve detail at a higher memory cost. We'll build a tiny pipeline that shows the whole flow. TF-IDF creation, direct truncated SVD compression, peeking at what terms drive a component, normalizing embeddings, and running a tiny search in the compressed space. The example is intentionally small, so you can focus on the mechanics that scale. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. We need to create the sparse TF-IDF matrix and measure how sparse it is before we compress it. This snippet builds the sparse TF-IDF matrix that creates the memory challenge. Scikit-learn, TfidfVectorizer, reads the tiny docs list, learns a vocabulary with vec.fitTransform docs, and returns X as a sparse matrix instead of a dense table. The important idea is that most document term positions are zero, especially when the vocabulary grows. Density measures how much of the matrix actually stores non-zero information, so students can see why sparse storage matters before adding compression. The output shows the matrix size and density, which sets up why direct sparse compression is useful. Now that we can see the sparse matrix, we need to compress it without first turning it dense. This example compresses X directly with scikit-learn truncated SVD. PCA-style workflows often become painful for text because centering can remove the sparse advantage, while truncated SVD is designed to work on the sparse TF-IDF matrix from vec. The call svd.fitTransformX learns two latent directions and returns C, a compact dense embedding for each document. N-components controls the output width. Increasing it can preserve more structure, but uses more memory, while decreasing it makes embeddings smaller. The output compares the original term columns with the new latent columns, making the compression visible. Compression can feel abstract, so we look under the hood at what a latent direction means in plain text. This code inspects what the first latent direction is paying attention to. A compressed embedding can feel mysterious, so vec.getFeatureNamesOut connects the numeric columns back to readable terms. svd.componentsum contains one weight per original TF-IDF term for the first SVD component, and argsort selects the strongest terms for that direction. This is not a full topic model, but it is a useful teaching view of the latent space. The output shows a few influential words, which helps students trust that compression still reflects text content. Before using embeddings for similarity, make lengths comparable so one long vector does not dominate scores. This snippet rescales each document embedding after truncated SVD. Raw SVD coordinates can have different lengths, and that can affect similarity comparisons when logger vectors dominate the score. Scikit-learn Normalizer applies norm.fit_transform_z, producing z-unit where each row has unit length. That makes later dot products easier to interpret as cosine-style similarity, which is common for text search demos. The calculation checks the first row length directly from z-unit. The output shows the embedding length is now 1, which prepares the compressed vectors for nearest document lookup. Finally, test the end-to-end flow by querying the compressed index, so you see the whole pipeline in action. This example turns the pieces into a tiny search baseline. The new query goes through the same TfidfVec, SVD, and norm objects, so it lands in the same latent space as the stored documents. Cosine similarity compares Q against Z unit and scores every compressed document without rebuilding the TF-IDF model. Scores.argmax selects the best match, keeping the final step small but complete. In a larger project, docs would be your real document collection, but the mechanics stay the same. The output shows the nearest document text, proving the sparse TF-IDF input became usable compact embeddings. In a real project, you would map the same steps over your dataset and store the z-unit matrix for fast lookup. That storage is small compared to keeping full TF-IDF matrices, and the runtime lookup is cheap. Use this technique when you want compact embeddings for search or downstream models, and you need to preserve sparse memory benefits during training. It's a good fit for mid-sized corpora and a solid baseline before trying heavier neural embeddings. One caveat: truncated SVD is linear and may miss deeper semantic nuance that larger models capture. A practical next step is to tune the dimensionality by increasing n components and optionally add TF-IDF n-grams to capture common phrases. Then measure retrieval quality on a held-out set. That single change often improves nearest neighbor accuracy while keeping the sparse training path. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.